All right, and next up, Matteo is going to be telling us about a function as a service choreographic programming language.
So, okay, this works. Nice.
Stay on the stage.
Here?
Yeah,
okay.
That's where the camera is.
Oh. Okay, let's not die here. Okay. Hello, everyone. So what I'm presenting today is a very early draft for a proposal for a choreographic programming language tailored to the realm of function as a service. This is part of ongoing research work done by me, Giuseppe De Palma, Saverio De Lorenzo, Jacopo Mauro, and Gianluigi Zavataro, who is not here today. Now, first of all, a bit of context. What is function as a service? Basically, it's the main subset of what is known as serverless computing. And like everything related to serverless computing, the main principle behind it is that we want the user to be as removed and as oblivious as possible to every concern, especially when it comes to deployment and administration of cloud resources. Now, when you picture a functional service platform, you can imagine the core components to look something like this. So when you want to create a function, what you do is basically you write the code and you add some metadata about resource usage and so on. And then you simply upload it through the API and it's stored in the function storage. Now, when you want to actually use the function, you can do so in a couple of ways. You can either directly contact the platform using the main gateway. So in a request-response fashion, you can do some like HTTPS request, and then you send an invocation. Or you can link the invocation of the function to some trigger events. So for example, the insertion of a file in a database or some event produced by an IoT device. Now, when the actual invocation happens, the platform asks the scheduler to find a suitable worker, where worker are the nodes that actually host the functions, to run the function itself. While the autoscaler handles the problem of spawning enough replicas of the functions to satisfy the load of requests that it's going to receive. Now, functions that are developed in this paradigm have several properties. So first of all, they're isolated. Since functions are basically arbitrary code that is executed on a remote platform, we have to separate them from the rest of the runtime and from each other. This can be done through containers, virtual machine, what have you, but you need to separate them. Second of all, they are short-lived. One of the main principles behind functions as a service is that we do not want to have idle resources that no one is using and someone is paying for. So when functions have finished their task, they are generally destroyed. This can mean tearing down the container or the virtual machine, but basically once they're done, they are removed. Therefore, they are stateless. Since they are short-lived, there is no notion of a long-running process underneath that can preserve somehow previous invocations. So each invocation, each instance of a function is completely independent from the others. And finally, they must be small in size. This is connected to all of the other properties. Since they're isolated, when I run them, I have to spin up the runtime and spin up the container or virtual machine that will host them. But since they're short-lived, I might have to do this several times. This means that if the function has a lot of dependencies or is very big in size in general, I will have to perform these costly operations multiple times, incurring in something that is known as a cold start. And we want to minimize the additional latency caused by this. Now, of all the concerns in function as a service, I will focus on two, and they are locality and workflows, where workflows is basically it's basically function composition in function as a service. Now, locality in function as a service boils down to where should functions be run? Where should the scheduler place the function, on which worker? There are many kinds of localities, and the three I'm focusing on are data locality, which is we want to run functions near the data that they use. We can see, as an example, we might want to run a function that contacts a database in Europe on a node in Europe. Then we have code locality. And code locality boils down to running functions near similar ones. And by similar ones, I mean functions that share dependencies. This boils down to minimizing cold starts. We want to reuse the dependencies that we have already downloaded and compiled as much as possible. And finally, we have co-locality. Co-locality is a bit more tricky and means we want to run functions that trigger others near the entry points. So, as I said, we can either invoke functions through the main gateway or through some pub subsystem through events. If a function is triggering other functions, we want to run it near the entry points that will trigger those functions. Workflows basically mean how should I compose these functions? And the reason why it's an important problem is because if you think about how small these functions must be and how we want to minimize the size and the amount of tasks that they perform, if I have a real application, this might mean developing tens, if not hundreds of functions. So I have to find some effective and efficient way to combine them. This comes down to either workflow languages, which is the most bare-bone approach. So I write my functions in some programming language, and then I describe in some other language the way they should be pipelined and the way the data should pass from one function to the other. Or a bit more sophisticated, having dedicated workflow engines. This is a solution that commercial platforms adopt, and it's basically an evolution of workflow languages. Instead of having simply a description that tells the platform, invoke this and then this and then this, we have a dedicated orchestrator, aside from the platform, that handles the subsequent invocations and also gives us some properties, such as ensuring that if a workflow fails at step 3, for example, the next time I run it, it will start again from step 3. Now, some issues here that arise are that, first of all, it's incredibly hard to infer locality from code in general. We have no unified way to say this function will call this service. We have no unified way of saying these functions share dependencies. And we have no unified way across languages and workflows to say this function will call this other function. We also have the issue that we do not have a unified language for workflows and functions. So if I have hundreds of functions that I need to coordinate, this can get pretty messy in the code base and also in following the logic of the entire program and the entire workflow. And finally, we have the issue of vendor lock-in when we talk about workflow engines. And vendor lock-in in this instance means that if I want to migrate from one platform to the other, I need to basically migrate the entirety of my workflows and also take into account the fact that I cannot guarantee that the semantics for the workflow engines on platform A and platform B will be the same, nor the guarantees. So I do not have basically a unified language and a unified way to express the behavior of my functions, how they should be composed and how they should be combined, and the locality principles that they need to be optimized or that they need to be satisfied in general. Which is where I introduce Pascal, which is the language that I'm talking about today. And it's very much in an early design phase. We do not have a complete specification yet. And ideally, we would like to have it be completely platform independent. So if you write something in Pascal, you can deploy it on any serverless platform and any fast platform by the means of projection, basically. Now, before I show you what the code would look like, I will show you a little use case that we will express in Pascal. I want to orchestrate the distributed training of a neural network for image recognition. Now, first of all, I want some way to trigger the workflow from the user or from some other event source. Then, I want, in the first step, to get images and labels from separate databases. So basically, I want to construct the dataset that I will use for the training. Then I want to split this dataset in separate batches, and I want to send these batches to separate workers to perform the partial fits. Then I want to take the results of all these partial trainings and integrate them in a final database to have the complete model. Now, the code would look something like this. I will get through block by block. Now, first of all, here we have the participants. They can be either stateful, stateless, or services. Now, stateful participants are standard processes. They are active by default, they are long-running, and they can exchange messages with each other, basically. Stateless participants are fast functions. They're identified by their name and the medium with which I can reach them. Here we can see, for example, F is reachable through the main gateway, while G and H are reachable through SNS, which is a notification service, and it's basically the pub-sub approach that I was talking about before. Then, and stateless participants are not running by default. So to have them actually do something, I need to contact them. And then we have services. Services we can assume to be long-running. They are passive, and we can interact with them in a request-response fashion. Services are external, so we have no concern in their implementation, and we basically treat them as external APIs. Here, the services are basically the three databases. So we can see that the DB1 and DB2, we can interact with them using get data, and DB3 with store data. Then we can import functions. We can import functions from certain libraries, and we qualify the imports on the several participants. So here, for example, we qualify zip as a zip at F. Then we import the fit function from the model library, and we qualify it on G. And then we import the integrate, and we qualify it on H. Now, the main function, of course, is the main behavior of the program. And the main block here is this, which is a request response that goes from user to F, and then returns all training jobs started. The important lines here are these. We can see how queries is a variable that is first on user, and then is passed through the gateway medium to F. And it's bound on F as queries. So basically, we send information from user to F, and we can see like this little bidirectional arrow across gateway means this is a request response. So we expect some data in return. At the end, we can see from F, we send back the all training job started to user. Now, the first part is, as I described, first of all, we take the subqueries from on F, and we send them respectively to DB1 and DB2 to get the labels and the images. This pipe operator, this little triangle here, means that we get the result of get data, and we pass it forward. In this case, passing it forward means that we bind it on a variable that can be either labels or images, respectively. Again, bidirectional arrow, so we are sending data to DB1, in this case the queries, and we are expecting data in return, in this case the labels. Now, in the for loop, what we do is we take each pair of labels and images, so we have batches of one pair, and we send them first to G through SNS, to perform the partial training. Then we take the result of that, which are model updates, and we send them to H through SNS. Then we integrate those with the model, and we send the result of this integration to DB3 using store data. Now, the important thing here, these are all unidirectional arrows, so this is just request operations. We do not expect a response. So F is not waiting for G to perform the fit before it goes on. So F basically just triggers G n times, and then it terminates. Now, the projected code looks something like this in a very Pythonish way. We can see the user code is very simple. We invoke F through the gateway, and we pass the queries parameter. F does exactly what I've described. We get the data according to the subqueries, and then we trigger G as many times as there are pairs in our dataset. And G and H have very simple behaviors, like G simply triggers H, and H simply stores the data, again, after they've done the partial fit and integration. Now, one cool thing that we can do with code that looks like this, when the language is structured like this, is that we can automatically extract the localities that I was talking about directly from the code, something like this. Extracting data locality basically boils down to seeing which participants contact which services. In this case, we know that F wants to be close to DB1 and DB2 because it's going to perform queries towards them, and H wants to be close to DB3. As for call locality, we look at which participants call each other, specifically which participants call which serverless functions. In this case, F wants to be close to SNS because it uses it to call G n times. And the same goes for G and H. And for code locality, we can see that G and H want to be close, specifically on the same node, because they both import from model. So they share a dependency. So we want to keep them close. Now, if we take these extracted localities and we combine them with some information that is given to us by both the provider and the user, in this case, the provider gives us topology information. So bandwidth from certain groups of workers to certain services. We can see here, group 1 has a high bandwidth towards DB1, but group 2 has no connection towards DB1. And the same way, for example, group 1 and group 2 have the same bandwidth towards SNS. And also user-defined constraints. So, for example, the user might ask us, please do not schedule F and G together, nor H and G together, nor G and G together. In this case, for example, since G performs the training part of the workflow, we can imagine it to be very computationally intensive. So we might want to leave it alone and have an entire node dedicated to it. Then what we can extract from all this is something that looks like this. Now, these are scheduling preferences that we can feed to the platform to tell the scheduler, please prioritize the nodes in this way. Looking at F, for example, we want F to be run on group 1, since group 2 cannot reach DB1. We want it to be run with a running instance of itself, if possible, because of code locality. And we do not want it to run with G, because the user asked that so. If this is not possible, because it's not always true that F can be run with a running instance of itself, then we simply ask it to be run on a compatible group of workers and without G, because the user asked us. G, for example, has no constraint on which workers it can be run on, because both of them can contact SNS and have the same bandwidth, so we have no preference. But we do not want it to run with either F, another instance of G, or H, because of the user constraints. And H follows the same scheme as F. This is written in a language that is a whole other branch of research that we're working on, but there are implementations that actually accept these configurations and actually modify the behavior of the scheduler according to what the user asks. Now, where do we want to go from here? First of all, of course, we want to have a complete specification and implementation of this language. We want to actually be able to test it. Then we want to compare it with the real-world scenarios, because we want to see what are the limitations, especially in terms of expressiveness, of a language such as this. And finally, we would like to explore different projection strategies to go back to the platform-independent argument. Since actually deploying on a serverless platform means adapting to the signature of the functions and adapting to the workflow language and or engine that the platform might use, we need to have different projection strategies for different platforms to make it truly platform agnostic and truly deployable. Thank you.
Okay, we have time for a question or two. I can start by asking one. And if the next speaker could come up and start getting a mic, then we can do that while the questions are going on. So I had a question about your the extracting scheduling preferences. Which of these are information that has to be user provided, and which of them are inferable from the choreography?
The left side, so the locality information is inferable from the code.
Okay.
Anti-affinity is not something that we can infer automatically as of right now, because it can also depend on some basic user preferences. And the topology information is something that should be given by the provider. Since the user cannot know it, we can expect the provider of the platform to actually give us some information about this.
I see. So the topology information you can't infer that from the code, but
not directly from the code. No.
Okay.
Yeah.
I see. Okay. Thank you. We have time for one more quick question. Anyone? Okay, let's thank Matteo again.